lecture over there.
Yeah. Okay. Is that what kind of university is that? Maybe you can introduce a little bit about
University. Yeah, thank you.
Yeah.
Thank you, Professor Bai. Thank you so much. I'm thankful to you, the participant, and thankful to Professor Chen and organizer, Professor Bai. Professor Ki Zhang is here, and thank you so much. Jake Spencer is here. Thank you all. You're here. I'm a lecturer in University of Peshawar, Pakistan. University of Peshawar is a general university where Department of Chemistry, Department of Physics, Department of, it's a general university. We are the general knowledge department. Most of the general knowledge departments are there in the University of Peshawar. And it has like the Department of Mathematics as well. And I'm a lecturer in Department of Mathematics in Peshawar University. Today my talk is based on multi-region segmentation, on generalized averages and one level set function. Contribution, some contributors for these talks are Noor Badshah from Engineering University, Professor Chen from Liverpool, Gulzar Ali Khan and Rushina from University of Peshawar. These are the contents of my talk. In first part, I will introduce some basic stuff related to my talk, and then two-phase segmentation models, like our general framework will be discussed. In part 3, I will go to my talk, like generalized, what are generalized averages, their properties, their level set representation. In part 4, we will move towards the data term, the generalized data term for multi-region segmentation to segment images. Then in part 5, some results will be displayed of that model, and part 6, selective segmentation result will also be displayed, and last, in the references will be given. Now, what is image? For example, if we have a grayscale image like MRI, CT scan, ultrasound, we have these images all around us. So, for being mathematician, what is a grayscale image for us? How we treat them? We can consider a grayscale image as a function of two variables. Like suppose we have a grayscale image. It may be like an example, but it may be MRI, CT scan. It may be ultrasound image. And of course, if we consider the function of two variables, so it will have then mathematical properties, whether we can apply mathematical theories. So it will have like a 3D plot. Image processing mathematically. I give two basic examples from image processing and in mathematics how we can deal them. Like suppose if we have a given noisy image. These are the two basic examples of image processing. One is from image denoising, and one example is image segmentation. I have taken these two fundamental examples from image processing. In image denoising, of course, we wish to get an enhanced version, a smooth version, a clean version of a given noisy image. But if we see it mathematically, we wish to obtain a smooth function which contains same features, same regions from a non-smooth image. And in segmentation, if we see, in mathematics, we want to separate foreground from the background with some closed curve. So in mathematics, you can see it is a sort of estimation of function. You are estimating a function over here, and in image processing, you see. So you can, connect the image processing and mathematics with each other. Now, there are several approaches for image processing. So one of the famous approaches for image processing is variational framework. What we do in variational framework for image processing, actually in variational approach, we design some energy functional. Most of the time we design some energy functional and we optimize it. Mostly, optimization or maximization problem are also there. Mostly minimization problems we see. So we minimize those energy functional, and the solution, the minimizer actually represent maybe the denoised version, or it may represent, like the boundary, or it may help us in some way in image processing. So we minimize some energy functional, and the minimizer is actually our solution in image processing. Now, actually, this talk is mainly based on image segmentation. In image segmentation, what we want actually, like we divide a given image into meaningful objects based on intensity, texture, and color. Like we divide images in image segmentation in meaningful objects. And another way you can define it is like dividing image into foreground and background. So this is the basic definition of image segmentation. A milestone model in image segmentation is by in variational framework is by Mumford Shaw. Here actually that in that model, in that technique, we wish to obtain a smooth version, a cartoonish type of version from a given image. So it is now easy to perceive it. For example, for computer vision or for other like for in medical science, now it is easy to pursue if we get a segmented image. So if we see this, how to obtain this cartoonish image, which is easy to understand, and how to get these edges, which play a very significant role for further information. This task to get this k and to get this solution z from a given image z naught. For that purpose, they designed that function, where here z denote the solution, that smooth image, that segmented image, and k, that solution represent the set of edges. This first term, this minimization, if we minimize this functional, so this this term will be minimized. This is called image data term, which actually forces that the result should be as close as possible to the given image z naught. This term, when it is minimized, when we minimize this ensure that in the solution we have in each region homogeneity. There should be homogeneity, and inside the edges, and edges should be prominent. And this term is the len term actually, which try to we get these edges more neat, more regular. There are several approaches in the literature on how to numerically solve it, or how to approximate that model. One of the particular case of that Mumford-Shaw model is the piecewise constant Mumford-Shaw model, in which we impose a condition on solution Z that this solution Z is piecewise constant in each region. So when we impose this extra condition on the solution, so the Mumford-Shaw model, this we get rid of that term, the derivative term, this vanishes, and we get a more simpler version. This is the piecewise constant Mumford-Shaw model. And here, it is now more easy to handle as compared to the general model. In this similar sequence, if we come to the piecewise constant Mumford-Shaw model restricted to two faces, when we restrict the solution further, like the Z solution, like it is piecewise constant in two regions, and we suppose that there are only two faces in an image. So the functional takes this form, where C denote the boundaries now in the image, and C1 and C2 are the piecewise constant values of that Z, and we get this functional from the Mumford-Shaw general model, or you can say piecewise constant Mumford-Shaw, and this is restricted to two faces only. If we consider this functional in level set formulation, this piecewise constant Mumford-Shaw model restricted to two faces, in level set formulation, this takes form in the equation number 4. What do we mean by level set formulation? In level set formulation, we consider the boundary as a zero level set of a function of one higher dimension. So now we are not going to find the boundary, but we search for a 3D function whose zero level set represents this C, where H is a Heaviside function. To replace this non-mathematical term, we got some implicit representation and didn't represent the Dirac delta function. So here, if you see the piecewise constant Mumford-Shaw model when restricted to two faces and its variance. So in simple case, it may work. like several variants of piecewise constant Mumford-Shah model and its several variants introduced from 2000 and till now. They may work in simple two-faces images. But if we move to multi-region images, like suppose if you see this is multi-region image, there are several regions, several intensities. So piecewise constant Mumford-Shah model, PCMS2, and its several variants, most of the variants, not all, maybe some works, but most of them will behave in this way. They will not detect each and every object in a given image, because you can see over here, if you see this hardware image, they will be not able to segment each and every object. This is PCMS2 and it's several, most of the variants. You can see over here a multi-region image and you can see the performance. And similarly, you see a clutter background image and you can see their performance, most of. If you observe here this particular image, here if you note the background is of minimum intensity. If we see here, the background is of maximum intensity. Here if we see the background is of mid intensity, neither maximum nor minimum, because in the foreground we have both minimum and maximum. So here background is of mid intensity. If we see over here, we have like a clutter background and you see their performance in each of these cases. Now, one way to tackle, one solution to enhance these several models for these cases, if we only focus this one, how we can enhance these all to capture these each and every object. So one way is, if we of course in PCMS2 and in their variants, most of them uses of course two constants to approximate. If we increase, just if we decrease, like in minimum intensity, one solution seems to be, if we focus, if we just decrease the C1 over here, like any constant you are approximating it, and if we decrease the other constant, like if we increase the two averages at which you are approximating them, just decreasing them, these all objects will be captured. In case of maximum intensity background, if in that case we only increase both the averages or both the constant at which you are approximating, so this all object will be captured. And similarly, now one question arises, can we increase the two constants C1 and C2? How? Can we increase two averages? Now it is really a strange question. Can we increase averages? Is there any way like we can increase or decrease averages? Let's see. How to increase or decrease averages? So answer for this is yes, we can increase and decrease averages accordingly. For example, how? Generalized averages can be used to increase and decrease averages. For a given grayscale image Z0, suppose we are given a grayscale image Z0, we consider it in a discrete sense. The generalized average is given by, this is generalized average, Z0, this is given image, take it some power beta, and divided by the same summation and power beta minus 1. This is called generalized average, and that was introduced by our work in, you can see in reference number 16. But similar concept can be seen in the analysis literature by Derek Henry Lehmer in their times in analysis, and you can see the reference for that. But that concept was similar to like ours, but he introduced it in analysis. And he named them as Lehmer mean. Now, next we analyze its properties. What are its properties? And really interesting properties. Let we have some positive numbers like x1, x2, x3 up to xn. We have positive number. So the more you increase beta, and so its behavior, you will move from center towards the maximum of the data set. You will get the maximum. The more you increase beta, where, like suppose the more we increase the beta, here, like 2, like 3, like 4, the more you increase it, the more you will deviate from the center and move towards the maximum. If you decrease beta, like 0, minus 1, minus 2, minus 3, so this average will give you the minimum of the data set. And you can see for proof 16. Now, we consider them in level set formulation. We bring it to the segmentation framework. The generalized averages inside and outside of an active contour in level set formulation are defined as follows. In similar fashion, we change these discrete averages to continuous framework. Same, summation is replaced by integrals and Heaviside. Similarly, 1 minus Heaviside and 1 minus you can see. So inside averages you can say and outside averages. Where beta is any real number, it is any real number. The above family of averages, we call them as AV family, average family. You can get the averages accordingly. Maybe some averages work for some and some averages may work for different images. If you see several well-known solutions or minimizers or particular cases of these averages, how? If you see, like suppose if you put beta 1 over here and here, suppose 1 and here, so we get these averages, and these are the minimizer of the piecewise constant Mumford-Shah model restricted to two faces, which is also known as Chen model. So you get these minimizer. If you put beta is equal to 2, you get these minimizers, these averages, and these were introduced in 7, and these are the minimizer of this functional, in which coefficient of variation was used instead of variance, and that model was used for selective segmentation. These are the so you can see several minimizers are its particular cases. Now we take some steps to utilize those averages for segmentation. We want to employ them for segmentation. We first consider now, so steps towards our generalized image data term. We first consider the following image data functional. We consider this functional. And here, like it is same piecewise constant Mumford-Shah model restricted to two faces, but here averages are not ordinary averages, but these are generalized averages. And we do minimization with respect to the level set function and not with respect to the averages. And it's also to get the generalized image data term, we consider its Euler-Lagrange equation to get our generalized GIDT. After some calculation with this equation number 12, we arrive at the following evolution equation named as GSB model. Like here, artificial time step is included, the Dirac data function is replaced by this gradient term, and this data term, after some calculation, we arrive at this and we normalize it with this quantity. So we get this, the model named 13 model, we called it as GSB model. Now, we move to the next slide and we analyze we do some analysis of this generalized image data term. What are, some properties. And you can also call as, like a sort of segmentation guarantee theorem. Like indirectly, it can, like gives a guarantee of some segmentation results. What it says about GIDT, let we have Q objects of, in an image with intensities I1, I2, I3, IQ. We have Q objects with intensities. The background intensity is denoted by IB. Background and foreground averages are respectively GC1 and GC2. So if the background intensity is maximum, like if you can see, like we have object intensities, and here you can see background intensity it is the maximum one. Now in that case, then for sufficiently large value of the parameter beta, mean that if you choose beta greater than 1, like 2 or 3 or 4, over here in this data term, so the sign of this function will be positive in the background and negative in the foreground. Mean that with the help of these signs, you can very easily segment the images. A sort of guarantee, it gives you a sort of guarantee. If the background intensity is maximum, you just choose beta greater than 1, all the object will be captured in a maximum intensity background. And this is the same part, means the same, but only difference is now background intensity is minimum. It says that with a small beta, like beta less than 1, this, the sign of the background and foreground will be different over here, and this can help you to capture each and every object in a minimum intensity background. The sort of segmentation guarantee theorem. this is a treatment for, like, we have discussed like maximum intensity background and minimum intensity background. That particular case, like, mid intensity background, we have that possibility as well. Like, suppose if the background is of, mid intensity, then what is the situation? Maybe we can handle, suppose, like alone with the same machine, with the same data term. But particularly for that, we have some further calculation. Like, suppose here the background intensity is neither maximum nor minimum, it is in between. In foreground, we have both minimums and maximum present. The background intensity in the mid, it is neither maximum nor minimum. So in that case, we modify our generalized image data term in this fashion. It is the product of these two functions, and these functions are defined in this fashion, in which one of them is off, like these averages are, one is off and one is on, like in this way. And we multiply them and we get our data term in this fashion for particularly mid-intensity background. And here for the parameter theta, we impose some constraint on this parameter theta, and we get bounds for it. Like, it is not difficult, we can get this theta very easily, where IQ represent maximum intensity in the image and IB represent the background intensity. This theta exists, and that is the sort of interval or range for that parameter theta. And these are some constraints. Anyhow, so we move towards the results of equation number 13, that how it behaves on multi-region segmentation. So let's see that model in multi-region segmentation. Okay, these are the main steps of our algorithm. Initialize the level set function, and these are like traditional steps. Evolve the level set function phi according to equation number 13. We regularize the function with Gaussian kernel, and we check whether evolution is stationary. If not, return to step number 2. And for further details, you can see our work 16. Now, here we give some test results of some latest and some good variants of piecewise constant Mumford-Shah model restricted to two phases. You can see, and this proposed model is denoted by GSB. First of all, we give a simple test, a simple two-phase test, and you can see all the four models work very well. But if we move to a multi-region image, a hardware is a hardware image, which is a multi-region image, you can see intensity changes over here. It is a maximum intensity background, and you can see the performance of these models, and you can see performance of GSB model, and we choose in this case beta 2. We just slightly increase the averages, like this empowers you to increase the averages. As the background is of maximum intensity, we slightly increase the averages, and you can see it has captured each and every object using only single level set function. Now we come towards the minimum intensity background. Here background is of minimum intensity. So when the background is of minimum intensity, we slightly reduce the averages. We just plug beta -1, like. And here you see the result. It is a sort of multi-region image. There are several regions, several intensities. You can see the result of these models and the result of GSB result. It is picking a complete object. It is a multi-region image. You can see the result. Here you see different intensities. We have one level set function, and you can see these variants. You can see they are behaving as they were modeled, and you can see the performance of the GSB model. And here, okay, here for mid-intensity background, we also have a value of parameter beta. Sort of, we try to make it automatic. Like beta is equal to 0.03 multiplied by number of pixels carrying maximum intensity. And we can try to make this parameter automatic. This is one of the attempt to, in this case, we can try to make this parameter automatic. In selective segmentation, you can see here we compare GCV and the GSB model. These are the two models. We are interested here in this kidney. And you can see this model is using this GCV model is using only arithmetic mean, only one choice for average. So this choice may not represent the object you want. So that is why it is some, producing some extra region as well. Automatic mean is not going to tackle this. And we have imposed a numerical constraint as well. And you can see slightly increasing the average. It is detecting complete edges. Similarly, here in colon, this image in which we are interested in the colon. And here, a minor, very small change here. You can see this GCV model has leaked and captured some extra region. Whereas if you see slightly increasing the averages, help us to capture exactly the edges. We have checked our model whether it is working in color. Is it maintaining its performance in color images? So few tests I have included here, like for example, we have multiple objects, various intensities, and results are compared with VV vector value Chen-based model. Here you see, yep, there are multiple objects of various intensities. So you can see the result. And here you see sort of inhomogeneity as well, and still the model is performing. Here we quantitatively evaluate what is the situation. Here if you see in this table, we use Jacquard similarity for that purpose. If you see images, we used maximum, minimum intensity backgrounds and mid intensity background. You can see here, if you see the GSF model, its value is more near to 1. This 0.98 is the mean value conducted on a sample of images carrying maximum intensity. Here, and this is the standard deviation. And here you can see that how this GSV model is performing. Like for example, if you see minimum intensity background images, you can see. And here we applied the same model on mid intensity background images, and you can see the mean value and the standard deviation. These are some references. Thank you very much.
You're very quick. Yeah.
Time is ours.
So we have a lot of time for question, comments.
Yeah.
We can discuss here. So just one comment. In fact, in a paper I did with Engelbart, so we consider the piecewise constant Badshah, and then in the omega I, so the energy is like it's like a zeta 0 minus CS square.
Yeah.
But we take the square equal to beta.
Okay.
And then we have one simple analysis which shows beta, if beta goes to infinity, and then the model is superior. But we never did any more analysis. It seems if you can also use your analysis to indicate, so replace the 2 there, by P. P goes to infinity.
Okay, P goes to infinity.
Yeah, we have some simple. We have one proposition show that if P goes to infinity, the model is superior than P equal to 2. Okay. But we never did any more analysis. Maybe you can use your
Yes, Professor. You mean that we can maybe also check that if suppose we place our P sort of P.
Yeah.
So maybe its minimizers turn out to be like these averages as well. For example, maybe these turn out to be the minimizer as well. So
if I give this this average, that will be very interesting.
Yeah,
so,
maybe that function.
I remember in that paper we have a lemma which showed that if P equal to infinity, and then you can the algorithm is much more stable with a zero and can segment more regions.
Okay. If suppose this P approaches to infinity.
Replace the 2 by something very big.
Very big number.
And then there was especially we found the case you see here. If you have an image, we have intensity C1, C2, C3, C4. If they are not far away from each other, if two of them are very close to each other, if P equal to 2, you will merge them. But if 2 very big, you can still separate them. That's what we did in that paper, right? So maybe you can try to see if you can
why not?
modify your analysis to cover that part as well.
Why not?
So we have a lot of time for comments and discussion. So come up with anything you want to.
You mentioned how you select beta automatically towards the end. It's 0.03.
Yeah, this one.
Why do you think the optimal choice of beta is linked to the area of maximum intensity?
We have tried, how to get that beta, we got sample of images of mid-intensity background, and we tried what is the value of beta turn out to be. And we found that relation. We tested our model on mid-intensity background. We tested on several images. And we tried to find a relation, like sort of function. We got the values of beta. So we got that relation, So based on several tests,
Right.
we were in search of such a relation. We were still trying to make it automatic, for the automatic. Yeah. So based on tests.
Right. So it's not explicitly linked to how the thing's defined. It's just.
Yeah. If you see 0.03, sort of ratio, several calculation is involved. You can refer to the 16. Yeah. But this is based on some experimental test. Yeah. We performed several tests. And we were trying to get some relation of beta and image intensities. So we found that beta is equal to 0.03 multiplied by number of pixels carrying maximum intensity. It's give you a way how you can, make it automatic.
Okay.
Yeah.
Is this size dependent then?
This beta.
Depending on the size of the image then, because it's more likely you have more points.
Yeah.
If you have a bigger picture.
Yeah, you're right. Yes.
Or you can
Yeah.
get it's
Yeah.
independent of size or something, right?
Yes.
So this beta is a regularization or it's a power? Because you use some places use the beta as
Yeah,
a
you're right.
regularization,
Yeah,
some
you're
places use the power.
Yeah, you're right.
This is the power. Right?
Yeah, here our model represent the power.
Okay.
Yes, in the paper we have called it as a beta.
Yeah,
So
yeah.
that is why.
Because in some earlier slides, the beta in the
It has a parameter on it. Yeah,
it's a
you're right.
regularization.
Yeah. This.
Mhm. Okay.
If a beta is more than 2,
Yeah.
can you still find out the functional?
If beta is equal to 2 over here.
Yeah, if you go back one here. Oh, yeah, here.
Yep.
You said if equals 2, this model is you call the
Yep.
key,
Yes, when beta is 2, when beta is equal to 2.
we call the COV, yeah.
Yeah, so this is a
What
coefficient.
about beta equals 3?
So
Can you find F?
that is you are trying. That is yes.
Okay.
If these are the averages, of course.
I see.
They are the minimizers of each functional. Yeah. Yeah. Yes.
Any other comments or suggestions?
Any question here?
How does it perform where the background is non-uniform?
The background is non-uniform. It's a very good question. Okay, so when the background is non-uniform, that model, if you see, it is for homogeneous foreground and homogeneous background. Yeah, but we can use some tools like multi-scale filtering to make the intensities homogeneous, and then you can use that model. But that model is not directly for inhomogeneous intensities, but you can use multi-scale techniques to get rid of inhomogeneity and then use that model. Yeah, and you can also use multi-scale filtering over here, incorporated in, but this is not directly. You can, incorporated that information, multi-scale filtering, to get rid of inhomogeneity.
If you had an example where the background wasn't homogeneous, you had an example with
The airplane,
Okay.
the
color
color
airplane,
image.
Okay.
color.
Color one.
The color.
Yeah.
Yeah, in that case, yeah, it has worked because if you see here, the background, the foreground is of minimum intensity. So here, then these averages is going to help you out because when the object is also, if it's a minimum intensity, if you just reduce your averages, so in that case, your averages is also going to fight with inhomogeneity because the object is here homogeneous intensity. Just reducing the average will help you out to capture the object. So, but it is not guaranteed that it will always work in homogeneous intensity. It is not guaranteed. In some cases, it can work like in this fashion. But if suppose like if foreground is inhomogeneous, background is also, so not guaranteed. Yeah, it is designed for homogeneous background, foreground. Anything else?
Okay, if not, we thank you for the talk.
Yeah.